the supports, they're basically just there to hold this thing up so it's suspended in midair, right? So we have suspended beams, okay? And we have, so let's call these the primary beams. And if we have something like this, okay, on top, we'll call that the secondary beam, okay? Oh, what did I just do? Okay, like that, okay. So we'll call that the secondary beam. We'll call these the primary beams. The idea is, remember that weird explanation I gave earlier with load paths? So you have like 3 toddlers and all that shit?
Yeah.
From,
Yes.
yeah, from week 1. The idea is that how loads flow is this dude at the top only has to take his own self weight. The person under takes both his own self weight and the person above, and the person at the bottom is taking all their self weight. Okay. And that's because the loads want to flow into the ground and dissipate. Okay. So in this analogy, the primary beams are, we just have 2 dudes. The primary beams are this guy at the bottom, okay? And the secondary beam is this dude at the top. Okay. So it's called secondary beam, I guess because it relies on the primary beam. And you can get into like tertiary beams and like quaternary beams or whatever it's called. But I don't, because then you can just go like 5-fold, 6-fold. It's actually really bad terminology. So I would call it, this is a primary beam. And anything that relies on another beam is a secondary beam. Okay. So in terms of industry knowledge, like if you guys want to do structural engineering, that's kind of the convention that people say. But what I want you to do, okay, is imagine this is loaded, this top beam, and it's like uniformly loaded. Okay. So this could be on a roof, and this is like a mech deck or something like that. So it has like heavy machinery equipment, like aircon, cooling units and stuff like that. And it's got a uniform distributed load. I want you to first draw the bending moment diagram for the secondary beam. And then following that, I want you to draw the bending moment diagram for the primary beams underneath it, okay? Okay, this film? Okay, so pretty much what I want you to think about is how the load flows through this, okay? So we said that this beam, right, which is a secondary beam at the top, it has a uniformly distributed load, right? Let's just say pinned, right? By the way, something that's pinned, this took me a while to realize as well when I was first starting at my job. But something that's pinned is basically, it allows rotation. So you see the self weight of this paper is kind of sagging it, like that. And I've got my 2 fingers here, but even though these aren't like literal pins, because if this is loaded, it freely allows rotation here, and it's supporting it vertically. That's something that's pinned basically, right? So this is technically pinned. You can't really see rotation in it, right? But this is a pin support because it rotates about here and here, okay? So basically that's a free body diagram, okay, like that. The shear force diagram, if you remember, is basically, you have the reaction, okay? So if this is, let's just do very clean numbers. So this is W is 10 kilonewtons per meter or something, okay? And the whole thing is L equals 10 meters, just for the sake of example. If we know the total force that's going down there is 100 kilonewtons, right? 10 times 10, okay? Basically, each of these is taking 50 kilonewtons each, like the reactions, that's what we're saying, okay? So the reaction, like if you do the sum of the moments and sum of the forces and equilibrium equations, you'll find that the reactions are 50 and 50, okay? Therefore, for shear force diagram, it goes up by 50, it goes over here, and then down with the point load of, oh, sorry. No, I did this wrong. Okay, sorry. It goes like that, because it's uniform. Okay, it's uniform. So it goes down 10 kilonewtons per meter, and then jumps back up 50. Okay, so that's 50, and that's 50. Right. The bending moment diagram, basically, in previous classes, you might have seen the bending moment diagram like going positive as up, but here we flip it because it is a better indication of how the beam sags, right? So again, going back to the paper thing, right? This is positive bending, and it's causing a positive deflection going downwards, right? So it makes more sense to flip the bending moment diagram to indicate the shape of Where's bending? It's also called tension positive convention or something. Okay, that's tension positive convention. So the tension side is the bottom side of the beam, and it's going down. Okay. So that's what the bending moment diagram looks like for that secondary beam. Now the interesting thing that I didn't realize when I was an undergrad is that when it loads the primary beam, what happens from here to here? This support is a reaction, okay? But that reaction now becomes a new point load for what it's supporting. So the thing that's supporting it, which is the primary beam, that reaction now becomes the point load. Right? So someone said before, is the free body diagram of the primary beam a point load? And you're right, it is a point load. So one of these primary beams is taking the reaction from before. So you remember the 50 kilonewtons from before? Yeah? That's now taking the 50 kilonewtons here. Does that make sense? Okay. So this is like how structures and like load paths and stuff work, right? It's pretty interesting. So yeah, now you've got the reactions again, okay, 25 and 25, because we've got two primary beams basically that's supporting your secondary beam. And they're kind of like splitting the load, I guess, right, if that makes sense. In terms of your shear force diagram, now instead of two triangles due to that slope, you've got what I drew before, okay? You've got this sharp jump in shear, and I'll explain that more in the shear topic, which is week 7, okay? But the idea behind shear and bending is this is vertical shear. And when you load a beam with transverse forces, right, you're not only inducing shear, you're not only inducing bending, but you're inducing shear, okay? And you'll see the interaction between bending and shear more in week 7, but the idea is you have to check for both for a beam, okay? And in the AS 4100, like the steel standards, they're under the same chapter. It's called like members subject to bending. It will be like all this stuff you have to do to check for bending strength, and then the subchapter is shear in beams or whatever it's called, right? So they're actually like closely interlinked, okay? And for your bending moment diagram, like you mentioned before, it's a triangle, okay? So now it's a triangle bending moment diagram that looks like that, okay? All right, do you guys have any questions about how that works? So the interesting thing about this, about how like, let's say you would design a roof structure for a building, right, is that this steel beam, the secondary beam, is bearing on the primary beam. We call it bearing because this contact, it's basically compression at this localized spot. So the bearing area is where the two surfaces overlap, right? And there is like some bearing checks and stuff like that involved, but generally, because this is bearing, you're gonna run into a problem, right? So if I want to put roof sheeting on top of these beams, which are in like the roof level of building, it's not gonna sit flat. Okay. So what we do a lot of the time is these are the primary beams, and now they're supported kind of like this. Okay. So for wood, right, it would be glue or whatever. But if you imagine these are steel beams, they'd have to be supported in a different way. Okay, but they're still supported, so you're still getting the same reaction. Okay, so this depends on this, which then goes into your columns and other supports and stuff like that. Okay, but what I want you to do is I want you to draw this connection. Okay, it's okay, no wrong answers. I'll explain how it will generally work. Imagine a steel I-beam running into another I-beam. So a secondary beam running into a primary beam. How does it look? Okay.
The same size.
Yeah, just pretend they're the same size. Yeah. Okay. Just draw what you think it should look like. How do you connect this secondary beam to this primary beam? Okay. So if I look at it that way, all right, and they're both I-beams, okay, that's our secondary beam. Okay. Right. And then we have our I-beam that's going into the page, because we're looking at it like that, right? So that's our primary beam. Right? The question is, how the hell do you connect these two things together? Because some people had the idea of you weld the flanges together, right? But then you got this big gap with the webs. So all the idea is, if you do that, firstly, remember the shear force diagram. I didn't draw it very well, but this secondary beam shear force diagram, remember it looked like this, okay? Plus, minus, okay? So here, at this interface, you have the largest amount of shear, okay? So basically, these welds are taking all that shear, okay? That's called a shear connection, right? And we'll talk about that in week 8, okay? But you can't rely on this, essentially, because the other thing is it's going to, when it bends, right? When this beam deflects like that, bends, you're basically dragging the I-beam with it. Does that make sense? So as that thing bends, you're twisting this, right? If you do weld that, which is horrible, because if you imagine a ruler, I don't really have a ruler, but imagine like a ruler-shaped cross-section, right? This is basically an I-beam, because most of I-beams meet is the web. Oh, not really, that's not really true. But the idea is, an I-beam is really bad in torsion, right? So, I-beam, if I twist it, it's gonna twist really easily, okay? But if I twisted a rectangular block, this is like a lot stiffer, but like, it's much harder to twist it, okay? So like hollow sections and stuff like that, much harder to twist. I-beams, incredibly easy to twist. And so this is like a really bad design, okay? No offense. But basically, if I were to do that again, okay? How I would do it is basically, okay, there's two ways to do it. I'll tell you the less optimal way. The less optimal way is you do a cleat, like you were mentioning before. So a cleat is a type of plate. It's also called, so this is a cleat. This is called a fin plate in some parts of the world, but in Australia we call it a cleat. So a cleat is just, it makes more sense as a fin plate, because like a fish has like a fin, and it's just like something that's sticking out, okay? But it's a cleat basically, right? And it's a pretty clever idea in general with plates and connections and stuff, to weld one side and bolt the other side, okay? So the idea behind that is, when it comes off the truck, right, this little cleat is not gonna mess with fabrication, right? On-site fabrication of steel is very much like these Steelfixer tradie dudes. They're like assembling Lego, basically. The pieces just have to easily come together, and you don't want them to weld, because welding is like very hard, and it requires like all these like certificates and stuff. You want to do everything. You want to do something called shop welding, which means in the factory, when they're preparing the beam, they have like qualified welders there, which are very expensive, and you know they like have like a very high rate and stuff like that. You want to do all the welding in the shop. You don't want to hire a welder specifically to go to site to weld like the other side of this, for example, right? So what you do is you just get these tradies, these steel fixers, to bolt, just complete the bolt component, okay? So you leave a bolt hole, and then you give them the bolt, or they supply the bolt themselves, and then they tighten the bolt, and now these two parts are connected together, okay? So one side generally bolted, the other side generally welded, okay? Yeah, so that's one way to do it, and the reason I don't like this way is because there's a large lever arm from here to here, okay? And so you're basically putting this plate into bending, right? It's like these dimensions, and you're basically bending it. Okay, so now this weld has to take a lot of bending, and the plate also has to take. Oh, sorry, the bolts also have to take a decent amount of bending. Okay. The more optimal design, and what you'll see a lot in industry practice, is something that's pretty close, but they do something called coping the flanges. Okay. So now they've just cut off the flanges of part of the the universal beam, and instead of this big gap between the two beams, now the web of the beam is close to this web of this beam, and you do the same cleat connection. In fact, it might be like a little bit shorter like that. So now you don't have as big of a lever arm. Okay. And this is the most optimal design. So this is, it acts as a pin support. Okay. This is pinned. And it's a shear connection. Because it's just taking shear forces. So, like, you know, the reaction from before. So it's just taking shear connection, whatever. Yeah, so that's called coping the flanges of the beam. So that's what you end up seeing as a detail everywhere in the real world for the beam to beam connection. Okay. So I might Google this to show you. Can you see that? So that would be your secondary beam. That would be your primary beam if it was like a bigger beam. So here I've drawn it as if the beams are the same size. So you have to cope the top and the bottom. But you only really have to cope the top because you want your, you know I was talking about the roof sheeting? You generally want the flat surface to be on the top, right, like this. And so the top of the beam has to be aligned, essentially.
Oh, so you just take a chunk of the flange,
yep.
so it's closer.
So remember what the flange does. Oh wait, no, you haven't learned bending yet. Okay, so basically what you'll find is, you know, moment of inertia calculations? The flange for an I-beam basically adds as much meat to the outside as possible, and that gives you a higher moment of inertia, so it's better against bending. But remember our bending moment diagram? This one. You got the least bending at the connection. So it doesn't actually have to take much bending here. It takes mostly shear here. Okay.
Is there another cleat like on the other side?
No.
No?
What you can see is all the connections.
So it's just on the one. Why is it on
Oh, right. Oh, I see what you're saying. You can do a double cleat, yeah.
Right.
I've got another picture, but okay, your question, Andy, is basically, would you put another cleat on the other side? You can, but the more cleats you add, okay, it's also a building tolerance thing, right? So if you're welding that in the shop and you weld the other one in the shop, you have to be able to perfectly slide the web of the I-beam in between. And if there's any gap, then you basically have to tension it with the bolts out. Anyway, so it's a little bit harder to build. But the reason you generally don't see that is basically the more connection you add, the more rigid it becomes and the less pinned it becomes. So if you only have one cleat on one side, it is more of a pin connection. Okay, you're adding more rotational stiffness basically.
Yeah.
The other thing that you might see is you might see an equal angle be used as a cleat. So instead of a plate. Now this is pretty common if it's not shop welded. So if you're in a situation where you need to site weld, so say that beam, that primary beam already existed, and then you're retroactively adding another beam there, right? This is better because an equal angle is already at 90 degrees. So it's harder to fuck up the weld on site, do you know what I mean? So if this already comes like this, right? Instead of like perfectly needing to align this and then weld it, this comes at a 90 degree angle. Oh great, we already know that this cleat is going to be at 90 degrees. Now we can weld on site more easily when it's like against a flat surface. Okay. Any questions?
I've got another question.
Yep.
So you see that secondary beam, it's already shorter than the primary? Like,
This one?
yeah, like, it's shorter than the
Oh,
primary.
it's less deep, yep.
Yeah, it's less deep. Why can't we just fit it within the gaps here, rather than having to take a chunk off the flange?
Yeah, it comes down to the fact that, remember, you want everything on the top surface to be even, so that when you put something on top, like a load or a roof sheeting or a concrete slab, they're taking the loads
Yeah.
all at once. Because if there's a gap, like that, and there's a concrete slab here, you know. Does that make sense?
Yeah.
So you cope it just so that the top plane is flat.
Yeah.
Yep. Okay, makes sense?
Is that why you'd also like, when doing it on the, like you wouldn't like bolt the top and bottom?
Oh yeah, so something I saw on Andy's drawing before is a plate that goes like on the top here, and maybe so you have an additional one at the bottom, and you're bolting like here and here and like through the flanges. Okay. So what you're doing there is you're making it fixed again. So this is pretty typical for like something like a splice connection or something that you do want fixed, because again, as this beam bends, it's going to rotate the I-beam, this other I-beam. So if you do it like this, where you add a plate at the top, it's going to make this connection more rigid, and therefore if this beam does bend, it's going to put this primary beam into torsion, which is not good. Okay.
For that example, would you need to take off the top flange and keep the bottom one as a whole piece?
Yeah, that's more optimal for if it's like unevened beam sizes. Yeah.
And because of that, would primary beams always be less deep than the secondary ones?
Not necessarily. Primary and secondary are more to do with what relies on what. It depends on the beam lengths and stuff like that. Bending moment, shear, yeah. So what I'm going to do is in the remaining time, I'll try to go through what I can with this. So I'll teach you roughly how it goes. In terms of the general flow of how you do the questions, it'll be very similar to how you're doing compression right now. Okay? So if you recall what you're doing right now, you're trying to work out the section's capacity, and then you work out the member capacity. Okay? So that's your section, let's say, it's an I-beam, and you're trying to work out how strong it is, right? After you account for local buckling and stuff. And then for the global capacity, or the member capacity, you're trying to work out its strength after buckling and stuff occurs, okay? That's axial buckling. For flexure, it's a similar process, but you work out the section's flexural strength first, okay? The section's capacity in bending, and then you work out the buckling strength, like accounting for buckling, all right? Okay, so, but first I have to teach you a bit about bending theory. Okay, so if you recall engineer's beam theory, right? We have a beam and it's being bent, right? For a simply supported beam, what happens is the top edge ends up being in compression and the bottom edge ends up being in tension. So that's a diagram of the strain. And the idea is that if you draw a line through the middle, right, we measure like end to end through the middle, through this like kind of curved arc shape, let's call it L. At the top, it's shrunk, right? So that's in compression. At the bottom, it's been pulled, so it's in tension, okay? Now let's analyze what happens to, not in this strain, but the stresses for a steel beam, okay? So steel beams, basically they have this material curve. And it's the same for tension and compression, okay? And this keeps going, but I'm not gonna draw the rest, okay? You have the elastic zone, and you have the plastic zone. All right, and you've seen this before because this is the FY and all that. We won't go to the FU, whatever. We'll just go to the point which it yields. And that point which it yields, it reaches a flat plateau in the material curve, and that's called the plastic plateau, right? Okay, the best way I can explain this, I came up with this analogy like this morning for solid mechanics because they're learning about something very similar. Imagine you're playing tug of war, right? 1v1, right? And basically this person's starting to win, right? They need to put in this much force and they're like putting in more and more force and whatever. But it's like plastic, right? So nothing's changed. Like the players, they both have a chance to win or something, let's just say. Yeah. So this person's pulling a bit more than this person, let's say, but that's all elastic. So elastic means it can bounce back, right? It can bounce back. But at this point where this person wins, do you know how like if you win tug of war, you kind of like you just kind of like end up falling backwards, and then if you lose tug of war, you like end up falling forwards. So that like momentum, right? Let's think of that as a plastic plateau. So the idea is once you reach a certain force, like this person's exerting, this person's just like their momentum carries forward, and you don't need to apply any more force in order for the whole system to move. Do you know what I'm saying? So same thing happens with steel, okay? Because with steel, you have the elastic region where, you know, there's an elastic deformation, right? It's like elongating and whatever as you're applying force. But at a certain point, the whole thing plasticizes like this, okay? And you see this like plastic necking and stuff like that happen here. But what happens is, at that yield point, you don't need to put in any more force in order for this like kind of cheese stringy effect to happen, right? As long as you apply a constant force, it's going to keep elongating. So that's a failure mode that happens in steel beams, right? Well, here I've drawn it in tension because it's easy to understand, but it happens in bending as well. Okay, so back to bending. The idea is, because the top and the bottom are the points which there's the most tension and the most compression. Okay, those points plasticize first. Okay, so if I'm bending, let's say this piece of paper. Okay, it won't work very well. Okay, that's not a good example. So if I'm bending this piece of paper, right, the top most fiber and the bottom most fiber of the paper are going to experience the most bending stress, right? In other words, tension and compression. Okay. And so they're going to reach the yield point first. Okay, the very top and the very bottom, right? So that's called first yield bending, the moment which the very top and bottom fibers have reached the plastic plateau. Okay. Now, if you keep bending it to this theoretical point, right, the whole thing becomes plasticized. The entire thing from top into the middle, like top and bottom into the middle, and that's called the plastic bending limit, or it's called like the point of plastic bending, and the whole thing's plasticized. Okay, and then in between there, like parts of it would have plasticized. So here, just from where my finger is upwards and from where my finger is downwards is where it's plasticized. Okay, make sense? So, yeah, and now we're going to talk about slenderness again. This is like section slenderness, right? So if you imagine this type of beam, like section, versus this type of beam section, right? We have like something that's very slender looking versus something that's very compact as a section, and in terms of the plates that make up the section, okay? The idea is that we can figure out the section slenderness, again, similar to how you've been doing the compression one, but there's like kind of different rules. And then, yeah, that's first yield bending. There's a formula to it. Right. First yield bending happens at this point, right? The moment is this thing called the elastic section modulus, Z, multiplied by the yield strength, right? So you can see similarities with this and how you've been doing it for tension and compression, because it'd be area multiplied by that, right? The idea is, the analogy is your elastic section modulus is basically your area but in bending. It's not really the same thing, but because like this thing gets weird, right? This thing is in millimeters cubed. Okay. So it's a little bit harder to visualize, but you think of it as the equivalent of area, but in the context of bending. Okay. Okay, and then I explain like how to calculate and all that stuff, but you'll see that in examples. I just want to run through it theoretically. Now, so that's first yield bending, right? Sorry. For plastic bending, we have a similar thing going on, except now we're multiplying it by a different quantity called S. S is the plastic section modulus. Okay. Thank you, Jen.
Yeah.
Okay. So, does that make sense, sir? So it's basically the amount of bending that I can take is multiplied by its material strength multiplied by these values, right? Your elastic section modulus and your plastic section modulus. Okay. So which one do we take when we're calculating the bending capacity in general? Okay, the answer is the section's bending capacity, right? Which was yeah, which was ms, right, is something called ze multiplied by fy, sorry. Okay. So why do we multiply by ze, right, which is the effective section modulus? Okay. Why do we multiply by it? It's basically, if you imagine it as like a number line, okay, over here we've got z, and over here we have s, okay. So z is whatever elastic section modulus that your shape has, and s is the plastic section modulus. Ze is some number in between. So it's effectively, what is its bending section modulus before it yields, okay? And it's a function of slenderness. It's a function of how slender your shape is, okay? And you can calculate it using lambda e. Lambda, like all these things basically. It's very similar to determining the compression slenderness of the section, right? This is local buckling and stuff that's happening, okay? So you're doing it for every type of section again, and you're noting down the yield value for every section again. And I mean, I'll explain all these things. I'll just explain these things quickly, right? So if you imagine your top flange in a beam and it's bending, okay? The idea is that we call that uniform compression at the top, because that flange is a very like small thickness, okay? So if that's our beam, okay, and this is our elastic bending stress, okay, and that's the neutral axis. The idea is that flange, right, and that's the stress distribution on the flange. It's basically a rectangle because it's so thin. Like, I know it's a trapezoid theoretically, but it's basically taking uniform compression because it's essentially a rectangle. Okay, so that's when you would take uniform compression in like a top flange, for example. Okay, if you had a sideways I-beam, right, in bending, that's a different story, because now this flange is taking like a more distributed amount of stress. Okay, so that's the neutral axis now. This flange here, it's now taking like a varying amount of stress. Does that make sense? Because it's taking the most stress here and then less towards the neutral axis in bending.
And that's even on both sides of the flanges?
Yep. Yep. But you would consider that flange and that flange the same when you're evaluating its plastic limit and yield limit on this table, okay? You kind of go through a similar approach for everything. These ones is basically how many sides is your plate supported by. So for a rectangular hollow section, they're supported by both sides, right? It's a very similar concept to the compression section buckling capacity. Okay, yep, so there's all these steps and all that, but effectively, what it all comes down to, and this is like an additional step, what it all comes down to, one sec, is here, okay? So once you figure out the slenderness, okay, you have your lambda s, and you compare it to whether it's going to plasticize or not. So, okay, sorry, basically on that timeline, right? So now we're looking at a new timeline. We have a slenderness, which is going to cause plasticizing, and we have a slenderness, which is going to cause yielding, okay? Or the first yield and the plastic point, right? Basically, for a compact section, so one that's very thick, like that, right? All the plates are very thick. All these elements are gonna reach plasticizing, right? So on a stress distribution, the whole thing can plasticize. Okay. Does that kind of make sense? Like, it can keep bending and bending and bending until the entire thing's plasticized. It can theoretically reach that point. So that's called a compact section. Okay. On the other end, for a very slender section like this, okay, the idea is that before it even yields, Sorry. Before it even reaches first yield, it can break. Okay. So, for example, this would like locally buckle out, like this web, or whatever portion of it could break before it even reaches first yield. Okay. So that's the slender thing, right? Now in the middle here is something called non-compact, and it's where it's yielded, but it won't fully reach plasticizing, if that makes sense. Okay. Let me redraw that. Sorry. So compact, just to recap, would be very fat like this. Okay. And it can reach full plasticizing like that, right? Non-compact, let's draw it like a little bit less fat. A good portion of it can reach plasticizing, but not the entire thing. Like that, okay? But parts of it have reached this yield amount, okay? So like maybe here to here has yielded, right? And here to here has yielded. So that's non-compact. Slender, a slender section hasn't even reached first yield. So first yield would be over here. Okay, before it breaks, due to its slenderness, okay? So those are the three types of sections you have to account for, okay? And ZE, ultimately the point of this formula to calculate ZE in these three cases is to basically, it's to work out what ZE is, right? It's to work out MS is equal to ZE times FY, right? ZE embodies everything that's embodies everything that's to do with local buckling, okay? For this shape. Does that make sense? Cool. All right, cool. Sorry, I know this is like a really like rough rundown of what's going on, and it's not going to make any sense until you actually like look through it properly. But yeah, there's all these notes on it. What I wanted to get to today, right, or at least like allude the concept of, because there's actually a lot to talk about. Like actually flexure's the hardest topic in this whole course, okay? And so I just want to shotgun everything right now to you so that you can fundamentally understand what's going to go on when we get back to it later, okay, in the course. Basically, you know how I mentioned that you have to calculate MS, right, which is briefly what I talked about, before you calculate MB, right? And MB is a function of buckling, okay? The idea is that buckling, when we're talking about axial forces, buckling is like that, right? We can kind of visualize it very easily. What's less intuitive is lateral torsional buckling, okay? Now this is a different type of buckling. So what I'm going to do is I'm going to, actually, could someone hold this? Or maybe you hold one end, you can hold the other end, okay? Sorry, hold it more towards that way. So if I apply a point load in the middle, right? This is quite a slender member, right? Like what do you think happens? It's going to start to fall out like that. Isn't that a bit weird? Why is it doing that?
Because it's more prone to buckling that way.
That's partly the reason. Okay. So this is simply supported, and I'm putting a point load in the middle. What's happening is which side's in tension and which is in compression?
Bottom tension.
Bottom's in tension. The top is in compression. So it's an uneven distribution of tension and compression, and we know that compression causes buckling, right? So the top it wants to buckle out, but the bottom wants to straighten out because it's in tension. Do you see this like weird phenomenon that's happening? And what happens? This happens when there's an uneven IX versus IY, basically, right? Sorry, you can stop holding that. Thank you. Lateral torsional buckling won't happen for a shape that's like more balanced like that. It's just for like shapes which have a large difference in their bending stiffness that way versus that way. Because that way, it's going to want to bow out, right? But this is what happens with I-beams all the time, okay? And what you'll find is that there's things later that you find out about called like full restraints, partial restraints, and lateral restraints, which are basically, do you remember how like the top is bowing out? It's basically like pinching the top, so it can't bow out in compression. Okay. What's weird is that was in compression. Oh, sorry. Yeah, like the lateral torsional buckling happened on the compression flange, right? I say flange as if it was an I-beam, but like on the compression side for a simply supported beam, which makes a lot of sense, right? But for a cantilever, okay, and you apply a downwards load to it, the compression side's actually at the bottom, and the tension side's actually at the top, okay? Because you can just see how it deflects is different, okay? So the bottom's actually in compression, so it's flipped, as opposed to a simply supported beam. So what do you think happens if I apply a downwards load on a cantilever, okay? What do you reckon?
The bottom part
You reckon the bottom will come out, right? Because that's intuitive, because it's the compression flange. But what happens is the top fucking comes out. Do you know what I mean? Isn't that a bit weird? The top comes out because for a cantilever portion of a beam, it buckles in tension, which is really strange. I don't know why it does this, but this is like a well-known phenomenon in like solid mechanics. It buckles from the tension side for a cantilever, okay? So imagine it's an I-beam, where we have a top flange and bottom flange. What we say is that there's a critical flange, okay? The critical flange is the one that's going to buckle out. So for a simply supported case, the critical flange is your compression flange, okay? For a cantilever, it's a tension flange, okay? Make sense? It doesn't make sense to me, but it is cool, right? It is interesting. All right, that's all I had for today. Good luck for your test.